We've got an invader problem that deals with a gram amount given, which is just makes you do a tiny extra thinking at the beginning, but nothing that you haven't done before. So let's take a look. Some stuff that the problem gives, it's actually a two-part question. First, it lets me know that I have a 1.75 gram sample of potassium hydroxide, all right? And it says that this sample is existing in 0.9 liters. So that's the given information from the first part. And it wants to know what is the pOH here. All right, well, I know in order to get towards a pOH, I would need a molarity, right? But molarity is moles over liters. So I've got liters, what I don't have is moles. So obviously these grams can convert to moles very easily, right? So I want to go from grams to moles of KOH. All right, make the diagonals match. When moles is compared to grams, it's 1 mole equals periodic table grams. So we'll go to the periodic table. K plus O plus H is 56.11. You can go verify. And when we solve this grid, multiply across the top, we're going to get, and divide by the bottom, we're going to get 0.0312 moles. All right, so there's the mole count from the grid, but I want to divide moles by liters to give me molarity, so we can just go straight ahead and divide by liters, which would be 0.9. All right, and this is going to ultimately give me a molarity of 0.0347. All right, so we've got a molarity of the solution. We, of course, are looking for the pOH. All right, hey, but check it out. We actually have the molarity of a base. So this pOH question is right up our alley because it matches. So I'm just going to go negative log of, it's a strong, so just of the strong sample of 0.0347, which will equal pOH. All right, which is going to equal 1.460. So that's the first part of that question. Then it says, all right, well, you had the 1.75 grams of KOH. It wants to know what if we are going to add that to a buffered solution. So we are going to take this KOH sample and we are going to add it to a solution that is already buffered with ammonia and ammonium, so a weak base and its conjugate acid. So as we get to the second part of the problem, it's an invader problem with hydroxide, right? Potassium hydroxide is the invader. So all I care about there is the hydroxide. That's what makes him strong, of course. So we are going to be adding him to the buffer. Now, the buffer contains ammonia and ammonium ion. So since we already have this buffer, I need to decide which part is the negative going to interact with. Well, the positive, of course. All right, so there's the interaction. So Bronsted-Lowry is going to have an H donate towards that base. We're going to get some water alongside some ammonia. Oh, there's a plus right there if you care. But anyways, of course, we expected ammonia to be formed because we knew that it would be, that's how a buffer works. All right, well then it's an invasion, so we need to compare the mole counts in a limiting reactant mindset. Now, hey, check it out. Look right here. I already have the moles of the given. That's why it says we're using the 1.75 grams. So we've got our moles here of 0.0312. All right, and that was the hydroxide. Now, the ammonium, we're going to have to look at the values in the problem. And it gives me some information here. It lets me know that it's a 1 molar solution. All right, so this 1 molar solution, oops, it's 3 sig figs though. All right, is describing both parts of the buffer. All right, and that is existing in 1.4 liters. All right, so all I have to do to get moles is multiply, of course. Molarity times liters is moles. So look, it's times 1. So I'm going to end up with 1.4 moles here. All right, water's not going to affect pH. And 1.4 moles here. All right, so let's take a look at who the big winner is. The smaller number. Uh-oh, the strong dude lost. That sucks. We're going to shift up over here. Don't forget. All right, so we have no moles of the strong left. If I do this subtraction, I have 1.37 moles of ammonia left. And if I do this addition, I get 1.43 moles of ammonia. All right, and you can check my sig fig work there. Look, I dropped that 0. Stupid teacher. All right, well, check it out. We have a buffer, all right? And we expected it to work out as a buffer solution. Still recording? Yes, okay. Because of the way the problem was written. So now we're going to go Henderson-Hasselbalch in order to identify. So remember, but having moles here is no bueno. So let's go ahead and divide by the total volume, which was the 1.4 liters, right? Because it says that we just dissolved these grams into these liters, right? It didn't take the earlier liters into account. So I'm going to divide both of these numbers by 1.4 liters. All right, and when I do that, we're going to get a couple molarities. I'm going to get an NH4 molarity of 0.979. Right, and that's for him. I'm going to get an ammonia molarity of 1.02. That's describing him. And now we can Henderson-Hasselbalch this guy to death. We have we're dealing with ammonia, so we need to know that the Kb value here is going to be 1.8 E negative 5. That's a given value. So now we can plug into Henderson-Hasselbalch. Now it's a Kb, so it's going to inherently give me POH. So make sure you have the Henderson equation in front of you, which is going to state that it equals PKB, P meaning negative log, of Kb 1.8 E negative 5, still following Henderson, plus the log of the ion over the weak. Look where the ion is. There he is. The ion gives me the top number. Whoa. Over the weak sample, the bottom number. All right. So we can go ahead and run that. We'll go negative log of 1.8 E negative 5 plus the log of 0.979 over 1.02, and I get a value of 4.727. There he is. All right. Now, this second part of the question, bye guys, is actually asking, it says, what is the hydrogen concentration? All right, so it's important that we realize that that's what it wants. So we've still got some work to do. To get to H+, I need a pH. So I know that these two numbers will equal 14, which is going to give us a pH of 9.273. And then, of course, my trick for getting to pH to H+ is to go 10 to the negative pH. And that's going to give me a final answer of 5.33 E negative 10 molar. You want to come wave to the people? You'll be famous forever. Are you ready? Are you ready? Are you ready? It's an upside down heat set, Daniel! Oh my goodness. Sorry, I didn't know we were going to be upside down.